Now the next function we're going to deal with is the exponential. Okay, the exponential is just this function e to the x. Okay, where e is this number 2.71828182845 and blah blah blah. It goes on forever. It's irrational. Okay? The decimal expansion of e is infinite and aperiodic. Okay. So again, where does this e number come from? Well, we'll see that later in the course. Okay, we'll see where this number e comes from. And why it is important. Okay? But so this definition of this function is e to the x. This implies raising this e to a power of x. Okay, so what does this mean? Okay, for any real number x. So well, we have n, a natural number, and I have e to the n. We know that this is just e times blah 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 times e, and there are n times here, right? We know that. So that's easy. If we have, but from this we get this interesting property n plus m, where these two are natural numbers. Then we have e times blah 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 times e times blah 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 times e, and all of this is n plus n times, right? But then we can take the first n and the second n numbers and separate them. Okay, so if we take this part, this is just e to the n, and the second part is just e to the n. So we've gotten to this very interesting quality: e to the n plus n is equal to the e to the n plus times e to the n. Okay, and from this it follows that, you know, e to the n is just e to the n times e to the n times blah 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 times e to the n. Okay, and there are n times here, n terms of e to the n, right? But we can really use this expression to write this like e to the n plus blah 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 plus n, and this is n times here, right? So in other words, we can rewrite it like this: e to the n times n. So we have again gone to another very important property of the exponentials. E to the n is just e to the n times n. Okay. Now, okay, so we have this is when we have natural numbers as the exponential. What happens when we have a negative number? How do we define this? Well, let us extend this property that we have just said, e to the n plus n is e to the n times e to the n. Let's expand it to include negative numbers. So let's say I have e to the n. Well, I can say this is e to the n plus n minus n, right? I can write it like this if I want, because this doesn't change anything, because n plus n minus n cancel each other out. Now I can take n minus m, so I have e to the n minus n times e to the n, right? So this is an extension of this formula. So if I divide by e to the n, I have e to the n minus m is just e to the n over e to the n. Okay, so now I have this for subtraction. Okay, now if I divide by e to the n in both sides, I have e to the n minus m divided by e to the n, and then I have 1 over e to the n. Now we have just said that this division we can rewrite like this: e to the n minus m minus n, right? But then n and n cancel each other out, so then I have e to the minus n. Okay, so this is the definition of e to the minus m, so e to the to a negative number, a negative, an integer number, negative number, okay? E to the minus m is, well, 1 over e to the m, okay? And then interesting numbers is that when I have e to the 0, I can write e to the n minus n, right? So this is just e to the n over e to the n. But these two things are the same, so this is just 1. So another interesting property of the exponential is that e to the 0 is 1. Okay? And let's see. So now we have seen natural numbers, we have seen integer numbers. What happens with rational numbers? Well, I can write e, okay, and let's see, I can write e to the n over n, right? This is just the same because this is e to the 1. E to the 1 is e to the 1 over n, so this is just e to the 1 over n to the n, right? We have said this before. But if we take the nth root of both sides, we have the nth root of e is just e to the 1 over n, okay? So when I have e to the 1 over n, this is just taking the nth root of e. And from this it follows that e to the n over n, so for any rational number, this is just the nth root of e to the n, okay? Okay, so now we have natural numbers, we have seen integer numbers, and we have seen rational numbers. Now what happens with the whole of the reals when the reals are irrational, for instance? Well, we know, and I don't know if I said this explicitly, but any irrational number can be approximated by a sequence of rational numbers. Okay, so if I have any number x, let's say x, that is rational, and I can take a value, for instance, let's say q1, that is greater than x, and a value p1 that is smaller than x. So p1 and q1, let's say, I'm going to write it like this, are rational numbers, okay? Now, because of the properties of the rational numbers, I can always find a rational number, that's greater than p1, but it's still smaller than x. And the same with q1, okay? And with p, I keep doing like this, and I keep doing like this. And so the definition of the real numbers actually involves this kind of definition. I can get a sequence of rational numbers from both sides that get me closer and closer and closer to this natural number, this real number. Okay. So now the definition of e to the x is just this thing, but applied to the exponential of these numbers. Okay, so we have a sequence, and we will see what sequences are next unit. Okay, so it's a sequence of here the exponential of rational numbers that we know how to compute. We have done it before, that get closer and closer and closer in the exponent to x. Well, the value of the exponential gets closer and closer and closer to the exponential of x. Okay, and then when we see sequences in the next unit, you will see that the limit, we call the limit of this sequence, is e to the x, and the limit of the sequence is e to the x2. Okay, we can define it in such a way that we are bracketing this number by a sequence of numbers that gets closer and closer and closer to it. Okay. Okay, so the main properties of the exponential, we have seen them now, so this is just a summary. The domain of the exponential is R. Okay, we have seen the input to this function is every number that we can think of. We can think of positive numbers, negative numbers, rational, irrational, whatever. It can always fit in this formula. Okay. Now e to the x is greater than 0 for all x in the real line. Okay, so this is kind of interesting. Well, it's easy to see because e to the 0 is 1, and then for instance, e to the n is just e to the 0 plus something, times something. We can make arguments like this to prove that the exponential is always greater than 0. Okay, I'm not going to do the proof here, the complete proof for this here, but it's not very complicated. Okay? E to the x is monotonic, strictly increasing, and then injective, of course. So yeah, that's easy to see again, because if you have x and y, you would see that, you know, e to the y is just e to the x times e to the y minus x, right? So if x and y are not the same, this thing is greater than 0, and this thing is greater than 0. Okay, so you have so this thing is greater than e to the x, sorry, so that's what I meant. Okay, so x is smaller than y, right? So that was my argument. Now fourth, we've seen this, e to the 0 is 1, and then e to the x to the a is e to the a times x for any a in the reals. E to the x plus y is e to the x times e to the y, and e to the minus x is 1 over x, e to the x. Okay, so these four properties, we've seen that before, and there are many important, so you really need to know all these properties belonging to the exponential. Okay.